Tonight, we're going to explore one of the most sobering questions in modern science. Not the question of whether humans can reach Mars, but the question of whether Mars can ever truly become a second home for the species that built its civilization on Earth. For decades, Mars has been presented as humanity's backup plan, the world we would go to if Earth became unlivable, the place where our species could start over. Politicians talk about it. Billionaires invest in it. Entire generations have grown up assuming that if we can reach Mars, we can eventually live there. But hidden inside that assumption is a possibility few people ever stop to consider. What if Mars is not difficult to colonize? What if Mars is fundamentally the wrong planet? What if the greatest obstacle is not technology, cost, or distance, but the possibility that the environment itself can never be transformed into something human beings can actually inhabit? The dream is familiar. A red planet remade. A backup world waiting for us if something goes wrong here. But the numbers tell a quieter, harder story. Earth's atmosphere presses down at roughly 100,000 pascals. Mars offers about 600, less than 1%. Standing unprotected on its surface is the same as standing 30 kilometers above sea level, in a sky where no human can breathe. The air that does exist is 95% carbon dioxide, with oxygen sitting near 0.1%. Effectively zero. Every breath, every degree of warmth, every drop of water has to be manufactured and defended. By the end of tonight, you're going to understand why that thin 600 Pascal atmosphere changes everything. How the absence of free air, free pressure, and free warmth turns colonization into a permanent survival experiment. And what this honest accounting tells us about the only planet that has ever truly belonged to us. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. That number is not abstract. Pascals are simply a measurement of pressure, of how hard the air pushes against everything it touches. On Earth, that push is constant and enormous. 100,000 pascals pressing in on your skin, your lungs, your blood vessels, every second of your life. You were built inside that pressure. Every cell in your body evolved to work with it, depend on it. Assume it would always be there. Mars offers 600. Think about what that number means physically. The best comparison is altitude. Climb high enough above Earth and the air thins. Atmospheric pressure drops. At the cruising altitude of a commercial aircraft, around 12 kilometers up, the air outside is already thin enough to kill you in minutes. Pressurized cabins exist for exactly that reason. But Mars is not at 12 kilometers. The pressure on the Martian surface is what you would find at roughly 30 kilometers above sea level, 100,000 feet up. No aircraft in regular service flies that high. No human being has ever stood unprotected at that altitude and survived. The air is not just thin, it is functionally absent. Stand on the Martian surface without a suit, and your lungs would try to breathe. They would expand. They would search for gas molecules to pull across the lung membrane and into the blood. But at 600 pascals, there are not enough molecules. The motion your breathing muscles make would draw in almost nothing. You would feel the effort and get almost none of the result. Your body would register this as immediate suffocation. But the pressure problem goes deeper than breathing. At normal Earth pressure, your blood stays liquid because the pressure surrounding your body holds it in place. Drop the external pressure far enough, and the dissolved gases in your blood and the fluids in your soft tissues begin to misbehave. Saliva on your tongue would start to bubble and evaporate. The fluid in your eyes would begin to dry. These are not slow processes. They happen within seconds of unprotected exposure to near vacuum conditions. Your chest would feel a collapsing sensation as the pressure differential between inside and outside your body becomes extreme. Loss of consciousness would follow within seconds, not minutes, seconds. Here is the thing people sometimes get wrong about this. They imagine that holding your breath might buy time. It does not. The problem is not only that you need oxygen, the problem is total pressure. The outside is near vacuum. Your body is pressurized to 100,000 pascals from the inside. Without an external shell pushing back, the body cannot maintain itself. A held breath changes nothing about that equation. So the pressure suit is not equipment in the way that a jacket is equipment. It is a life support shell. It holds a miniature version of Earth's atmosphere tightly around your body. It keeps the pressure constant. It stands between you and the vacuum outside. And it must work flawlessly. Not mostly flawlessly. Flawlessly. Every connector, every seal, every seam, every glove must hold. Here is where the failure modes get important. A small breach in the suit does not give you time to react. The air rushes out. The outside rushes in. The equalization happens fast, and it happens in your direction. A cracked connector at the wrist. A torn glove from a sharp rock edge. A failed seal at the helmet joint. Any of these is fatal within seconds. Not injuries. Fatal. The suit is the only thing keeping a human body alive on the Martian surface, and it is doing it while you walk, work, bend, carry, and expose it to a landscape that has never once been kind to fragile materials. That is the first problem. Just the pressure. Just the number 600. But here's where it gets strange. Even if the pressure problem was somehow solved, even if you could walk outside without a suit, even if the air were thick enough to breathe, you still could not breathe it. Because the gas itself is wrong. On Earth, the air around you is roughly 21% oxygen. That oxygen is what your cells burn alongside sugars and fats to produce the energy that keeps every function in your body running. The rest of Earth's atmosphere is mostly nitrogen, which is largely inert inside the lungs. Your body ignores it. It passes in and out with each breath without doing anything to you. Earth's air is almost perfectly calibrated to be useful without being toxic. Mars' air is 95% carbon dioxide. Oxygen sits near 1/10 of 1%. Effectively zero. Not a small problem. Not a rounding issue. The gas that makes up almost the entire Martian atmosphere is the gas your body produces as waste. You exhale carbon dioxide because your metabolism generates it, and your blood carries it out. You exhale it to get rid of it. Mars has taken that waste gas and made it the dominant constituent of its sky. This matters in two ways. The obvious way, there is no oxygen to breathe. Fill your lungs with Martian air, and you would be filling them with a gas that does nothing useful for your metabolism. Suffocation would follow as surely as it would in a room full of nitrogen or helium. But the second way is worse. Carbon dioxide is not inert at elevated concentrations. It is a toxin, a graded one, which means it gets worse as concentration rises, and the brain is tuned tightly to how much of it is in the air. A small increase, a few hundred parts per million above normal indoor levels, causes stuffiness and a slight increase in breathing rate. Your body notices. A rise to a few percent of the total air produces headaches, confusion, and a rising sense of panic. The brain begins misfiring because CO2 saturation in the blood interferes with the chemistry of nerve signaling. Around 10%, unconsciousness follows within minutes. Mars offers 95%. So consider what happens if you try the obvious workaround. Stay indoors. Pump Martian air into a habitat. Compress it to Earth-level pressure so the bodies inside can function normally. But the logic sounds reasonable until you run the numbers. You would be filling a sealed room with a gas that is 95% poison, compressed to the pressure at which that gas becomes dangerous enough to kill. The room would not be breathable air at livable pressure. It would be a pressurized chamber of concentrated carbon dioxide. The pressure would be right. The chemistry would be lethal. To make breathable air on Mars, you cannot use what Mars provides. You have to manufacture the air from scratch. That means stripping carbon dioxide out of every breath of habitat air continuously, through chemical scrubbers that run on power and consume materials. It means splitting molecules to produce oxygen, either by electrolysis of water or by chemical reduction processes, both of which are energy hungry and equipment intensive. It means importing or producing nitrogen or another inert buffer gas, because a pure oxygen atmosphere at even lower pressure creates its own set of fire and toxicity risks. This is not a one-time engineering problem you solve at the beginning and then forget. It is permanent, continuous, industrial-scale life support. Machines running every hour, consuming power every hour, wearing out and requiring maintenance every hour. The moment the system slows, the air composition inside the habitat drifts. Carbon dioxide builds, oxygen drops. The humans inside begin to feel it first as fatigue, then as confusion, then as something worse. And all of that, the pressure problem and the air problem together, exist before you have asked a single question about temperature, radiation, water, or food. The hardest part is not that these problems are unsolvable. Engineers have answers, at least partial answers, to all of them. The hardest part is that every solution requires a machine, and every machine requires power, and every power system requires maintenance, and every maintenance step requires a human who is already dependent on all the other machines to stay alive. The web of dependencies runs deep from the very first breath, and pressure and air composition are only the beginning. Water is the next question. If the air must be manufactured, if every breath depends on a machine running correctly, then the natural next thought is this. At least Mars has water. We have seen the headlines. Ice at the poles, buried ice in the mid-latitudes, frost forming on rocks. The planet is not completely dry. So can we use it? Here is where the surface of Mars does something that no headline quite prepares you for. Liquid water cannot survive freely on the Martian surface. The problem is pressure. Mars sits right at the boundary where water refuses to stay in its liquid phase. At temperatures between 0 and 20 degrees Celsius, the range where you might actually want to be outdoors and work, a puddle of water does not simply evaporate slowly the way it would on Earth. It either freezes solid or flashes directly into vapor. The thin air does not push down hard enough to hold it in between. Water skips past the liquid stage altogether and chooses one of the other two. There are no Martian lakes you can walk to with a bucket, no rivers, no rain falling on crops, no groundwater you can pump from a well and use directly. The water exists, but it is not available, not in any sense that matters to a living human body. What Mars actually has is frozen ore. The ice is locked in the ground, mixed with dust and salts and rock, buried under regolith at temperatures far below freezing. To get water from it, you do not dig and drink. You run an industrial chain. You drill into the ground. You heat the frozen material from very low temperatures to melting. You filter out the salts and perchlorates and contaminants that would otherwise be toxic. You pump the result into tanks. You repeat that process continuously, every day, because the colony is drinking and breathing and growing food around the clock. A Martian water supply is not a lake. It is a production plant with drills, heaters, pumps, filtration systems, and tanks, all of them running on power, all of them subject to failure. If any part of that chain stops, the water supply drops. Everything wet on Mars lives inside pipes and pressurized rooms forever. Water never gets to be part of a natural cycle. It is always manufactured, always contained, always dependent on the same web of machines that already holds the air together. And this is where the sealed habitat begins to feel less like a solution and more like a narrower version of the same problem. It is true that humans can live inside a pressurized habitat with a carefully controlled gas mix. The pressure can be held, the oxygen fraction can be maintained. In theory, you are safe inside. But the word safe requires that machinery inside that habitat perform without drift, indefinitely, in a place where you cannot simply open a window if something goes wrong. Consider what happens when a CO2 scrubber runs slightly below capacity. The scrubber is the system that removes exhaled carbon dioxide from the habitat air so it does not accumulate. If it underperforms by a small margin, the CO2 concentration in the room begins to climb slowly. Not quickly, slowly. The first thing people notice is tiredness, then a dull headache, then a vague anxiety they cannot attribute to any cause. These are not dramatic symptoms. They feel like a bad night of sleep, or a difficult day, or the early signs of a cold. By the time anyone thinks to check the air composition, the levels inside may already be in a dangerous range. On Earth, you open a window. On Mars, the outside atmosphere is the problem. There is no outside to retreat to. The machinery must be found and fixed while the air inside the room continues to drift. The planet does not provide a safe default. The default is lethal. The habitat is the only thin line between the inhabitants and that default, and it holds only as long as every system inside it runs correctly. But the surface of Mars refuses to give something else as well. Something more fundamental than water. Something you feel before you even think about chemistry. The cold. Mars is not cold the way a winter morning is cold. The average surface temperature across the entire planet is roughly negative 60 degrees Celsius, which is about negative 76 degrees Fahrenheit. That is not a polar cold snap. That is the baseline condition for the whole world, all year, at all latitudes, as the starting point before anything unusual happens. Standard laboratory freezers used to store biological samples typically operate around negative 20 degrees Celsius. Mars is 3 times colder than that as a routine matter. Near the poles in winter, temperatures fall below negative 120 degrees Celsius, negative 184 degrees Fahrenheit. At those temperatures, rubber stops behaving like rubber. Standard lubricants used in machinery and joints become thick and sluggish and eventually useless. Metals that are perfectly reliable at Earth temperatures begin to behave differently. Engineering for a cold place on Earth means engineering for a limited period under unusual conditions. Engineering for Mars means engineering for those conditions as the permanent normal, everywhere, always. But something else was happening. In the equatorial regions, in direct sunlight in the middle of the day, the surface temperature can reach positive 20 degrees Celsius, which is about 68 degrees Fahrenheit. That sounds comfortable. That sounds like a mild spring afternoon. And then the sun sets. And by dawn, the same patch of ground has fallen to negative 70 degrees Celsius, negative 94 degrees Fahrenheit. A swing of roughly 90 degrees Celsius within a single Martian day. Not across seasons, not across months, within 24 hours. Every sol, this swing happens again. Every sol, the habitat walls, the pipes, the airlock seals, the rover joints, the cables, the structural connectors, and the suit components all contract in the deep cold of the night and expand again under the warmth of the day. Metal and plastic and composite materials do not expand and contract at identical rates. Every joint between 2 different materials flexes slightly differently from the other. Over time, over hundreds of sols, over years, those tiny differences accumulate. Micro cracks develop in places you cannot see. Seals that were airtight begin to develop the very first signs of fatigue. A component rated for a certain number of pressure cycles may be reaching the end of its rating before anyone has thought to inspect it. The cold does not destroy things quickly. It works slowly, patiently, invisibly, until something gives. Most people's intuition about cold air and heat loss runs in one direction. Thinner air, like on a high mountain, should mean less heat transfer. Less air to carry warmth away from your body or your habitat. That intuition is reasonable on Earth. On Mars, it is dangerously wrong. When air is too thin for normal convection to work efficiently, the 2 dominant paths for heat loss are radiation and conduction. The habitat radiates heat as infrared light directly into the black sky. That sky is the near absolute zero coldness of space, with only a thin membrane of cold atmosphere between the two. And the habitat sits on frozen regolith, ground that acts as a massive thermal sink, drawing warmth downward from anything in contact with it. The thin air does not protect the habitat from heat loss. It removes convection as a player and leaves radiation and conduction to do the work instead, both of them dragging heat away continuously. To hold a habitat interior at roughly positive 20 degrees Celsius, against an environment sitting at negative 60 or colder, heaters must run without stopping, not occasionally, continuously. They are always fighting to replace the heat the habitat loses to the ground and the sky every single hour. That is a permanent electrical load that the power systems must carry before powering anything else, before running lights or water pumps or air processors or communications. Now, consider what happens if power drops. On Earth, if a building loses its heating system in winter, the interior temperature falls slowly. Hours pass before the rooms become genuinely dangerous, giving people time to find blankets, find another heat source, call for help, or move. The building holds its warmth because the outside temperature gap is relatively modest, and the insulation has time to work. On Mars, the temperature gap between inside and outside can be 80 or 90 degrees. The conduction path through the floor to frozen regolith is always open. The radiation loss to the sky continues regardless of whether the heaters are running. A power failure does not give colonists hours of gradual cool down. The interior begins tracking the outside at a rate that compresses the emergency timeline dramatically. Pipes carrying water freeze solid and burst. A burst pipe in a habitat is not just a maintenance problem. It is a pressurized system rupturing in the same enclosed space where people are breathing. Mechanical failure and life support breach arrive simultaneously. And then there is something Mars does on a planetary scale that has no real equivalent in ordinary cold climate engineering. In winter, especially at higher latitudes, the temperature drops low enough that carbon dioxide begins to freeze out of the atmosphere itself. The main gas in the Martian atmosphere turns into frost on the ground. The total mass of gas in the atmosphere actually decreases during winter as CO2 solidifies and falls. In spring, it sublimates back, returning to gas and re-entering the atmosphere. The planet breathes in and out each year in terms of total atmospheric mass, and with it, surface pressure varies. The outside vacuum is not even a stable number. This is not a small variation. The atmospheric pressure at any given location on Mars shifts meaningfully across seasons. Habitats and suits designed around a specific pressure differential between inside and outside see that differential change over the course of the year. Pressure sensors, valves controlling airlocks, and emergency vent systems must all account for seasonal variation without drifting into dangerous calibrations. Meanwhile, the CO2 ice forms and disappears on the ground itself. As ice forms, it pushes soil upward in the process called frost heave, the same process that buckles roads and breaks foundations in cold regions on Earth. But on Mars, it happens with both water ice and CO2 ice, and it cycles on a yearly schedule, lifting and settling the ground methodically. Foundations flex. Pipelines crossing that ground develop stress points at every location where the soil moves, and the pipe does not. The picture that emerges is not a cold place. It is a planet whose baseline condition is a global deep freezer, whose daily pattern imposes violent thermal cycling on every component, whose atmosphere loses heat aggressively through radiation and conduction rather than holding it in, and whose air itself freezes out and refills on a seasonal schedule that changes the pressure outside every single year. This is not cold like a difficult winter. This is cold as a permanent, active, structural force pressing against everything humans would build and wear and breathe inside. And the challenge of radiation, the fourth major threat to survival on Mars, sits on top of everything the planet has already imposed. Radiation is the fourth threat, and it presses against every habitat wall the same way the cold does. But before we follow that thread, consider what has already been established. The air is wrong. The water requires a factory to produce. The cold is a permanent structural force. And none of that has yet accounted for what gravity does to the body that lives inside those systems. The intuition is that lighter would be easier. Less weight on the joints. Less strain on the back. On a short visit that might even feel true. But over years, lower gravity does not spare the body. It quietly disassembles it. Here is how gravity shapes a human being on Earth. Everything that evolved in us, bone density, muscle mass, the geometry of joints, the pressures that push blood from the feet back toward the heart, all of it calibrated over millions of years to one number. 1g, 9.8 meters per second squared. Gravity is not just a number that affects how heavy things feel. It is the constant force that tells bones how thick to be, tells leg muscles how strong to stay, tells the heart how hard to push against the fluid column standing between the ankles and the brain. Remove it or reduce it, and the body reads that as a signal to let go. Mars pulls at roughly 0.38 g, 3.7 meters per second squared. A person who weighs 70 kilograms on Earth keeps exactly that mass on Mars, but their skeleton, their heart, and every vessel in their body only feels about 26 kilograms pushing down through them. 57 pounds. That is the load the bones carry. That is the signal the body receives every hour of every day. We know what happens to bodies in low gravity. The International Space Station has given us years of data from astronauts in weightlessness. Without a strict and demanding exercise regime, bone mass drops at roughly 1 to 2% per month. Leg muscles shrink because they are no longer needed to push against a heavy load. The spine, freed from compression, slowly lengthens. That sounds appealing. It is not. Lengthening spines create back pain, disc problems, and nerve pressure that can persist for months after return to Earth. But the reality was different. Mars is not zero gravity. It is not the clean, understood environment of the space station. Mars is an in-between, a permanent, untested regime that no human being has ever lived inside for years. And we do not know what decades at 0.38 G do to a human spine, to hips, to knees, to cartilage. We have models, we have extrapolations. What we do not have is data. The possibilities are not reassuring. Bone loss may slow compared to full weightlessness, but never stop. Joints may remodel in unexpected shapes, under loads they were never designed for in that configuration. Vertebrae may compress differently, or fail to compress enough, producing a spine that is neither Earth normal nor zero-G adapted, but something else entirely. Discs may degenerate faster, or in patterns no Earth physician has seen. The plan at this stage is essentially this. We will find out when people are there. In an environment where evacuation is impossible and emergency surgery means a small pressurized room with limited instruments. That is a dangerous kind of experiment. The skeleton is only part of the problem. The cardiovascular system is the other part. On Earth, gravity creates a fluid column running from your head to your feet. Roughly 1.8 meters of blood and interstitial fluid in a standing adult, all of it pulled downward. Hearts, blood vessels, valves, and pressure regulation systems evolved specifically to work against that column. The heart pumps hard enough to push blood upward against gravity. Vessels in the legs use muscular contractions and one-way valves to assist return flow against the downward pull. The whole system is tuned to that specific force. In orbit, that column disappears. Fluids shift toward the head. Astronauts develop puffy faces and congested sinuses. Their legs thin out as fluid drains upward. Some return from long missions with measurable changes in heart shape and size, the muscle having adapted to a lighter workload. A small number develop vision problems from elevated pressure around the brain. Mars does not remove the column, it reduces it. Not fully, not to zero, somewhere in between. And that in-between regime has never been studied in a human being for more than a few days. The predicted effects include blood pressure profiles that no cardiologist on Earth would recognize as normal, ankles that never feel heavy, a head that always carries slightly more fluid than it should. Over years, the heart muscle may reshape itself for a weaker gradient. Vessels may respond to chronically altered pressures in ways that produce long-term rhythm disturbances, or tissue changes, or novel cardiovascular diseases with no known treatment in Earth medicine, because they would have no equivalent in Earth medicine. The harder question still is, children. Animal experiments in partial gravity and rotating systems have already shown that development is sensitive to gravity. Mice and fish raised in altered gravity fields develop bones that form differently, muscles that do not bulk to normal proportions, and balance organs that calibrate to whatever force is present during growth. The inner ear, which tells the brain which way is down, wires itself to the local gravity, not to Earth gravity, to whatever is there. A child born on Mars would grow up with bones building themselves for 0.38 G. The spine would grow under that load. Hips would develop around joints never designed to bear Earth weight. The heart and vessels would tune their geometry to the smaller gradient from the first beat. Every calibration the body makes during development would treat weaker gravity as the baseline, as normal, as correct. Returning that person to Earth would not feel lighter on the way. It would feel like weight had been added. Every step like walking with a permanent heavy backpack they had never trained to carry. Possibly tolerable for a short visit with medical support. possibly not tolerable at all for the skeleton and organs underneath. What this means quietly is this: the vision of a multi-planet species imagines humanity moving freely between worlds, carrying the same biology from one gravity well to another. But the biology does not stay the same. A person born and developed at 0.38 G may be biologically locked to Mars, not by distance, not by cost, by their own skeleton and cardiovascular system. Earth and Mars may produce human beings who are permanently unable to live in each other's gravity without medical intervention or without harm. That is not a multi-planet species in the sense the dream imagines. That is two branches of humanity growing apart on a timeline measured not in generations, but possibly in the first generation. The instinct is to solve this with exercise. Train harder. Build the bones by loading them artificially. But Mars gravity caps what the body weight provides. A 70-kilogram person moving through normal daily activity on Mars puts only about 57 pounds of force through their bones. To approach Earth-equivalent skeletal loading, the exercise machines must supply the missing load directly. Weighted vests that pull downward, treadmill harnesses using strong cables to simulate gravitational pull, resistance platforms designed to exceed what natural gravity supplies. To truly approximate the loading profile of a life lived in 1G, rotating exercise facilities may be needed. Rooms that spin fast enough to generate artificial gravity during workout sessions. All of that means more mass, more power, more systems to maintain, more failure modes on top of the failure modes already piling up, and exercising with artificial loads on a skeleton that has already lost bone density in an environment with limited imaging equipment, no nearby surgical theatre, and no physical therapy infrastructure, requires walking a precise line, hard enough to fight the loss, gentle enough not to produce the fracture, the tendon tear, or the spinal injury that would be catastrophic inside a sealed habitat. The body, in other words, is not a passive passenger on a Mars settlement. It is another system that requires continuous maintenance, another system that degrades in Mars conditions, another system without a reset button, and radiation, which has been waiting through all of this, adds to the biological accounting in ways the body cannot exercise its way out of. Radiation works from above the way gravity works from below. Gravity quietly unmakes bone and muscle and the calibration of the heart. Radiation quietly unmakes something smaller and more fundamental. It reaches into cells and damages the instructions inside them. On Earth, most people never think about this, and they don't have to. The planet handles it for them. Earth carries two great protectors. First, a global magnetic field, generated deep in the molten iron core, that deflects charged particles streaming in from the sun and from the wider galaxy, bending them away before they reach the surface. Second, a thick atmosphere, roughly 100 kilometers of gas overhead, that absorbs and scatters what the magnetic field misses. Together, these two layers reduce the radiation environment at ground level to something the human body can manage across a lifetime. A typical person absorbs around 3 millisieverts of natural background radiation per year. That number is low enough to be a footnote in an annual medical checkup. Mars has neither of those protectors. The global magnetic field essentially vanished billions of years ago, when the Martian core cooled and stopped generating it. What remains are small, patchy magnetic remnants locked into ancient rock in a few regions. They cover almost nothing. The atmosphere, already less than 1% of Earth's thickness, does some filtering, but not much. The result is that the radiation environment of deep space sits at the surface. It does not wait above the atmosphere. It is not an orbital astronaut's concern. It reaches the ground, the rock, the dust, the suits, and the people. The baseline comes from galactic cosmic rays. These are high-energy particles, mostly protons, accelerated by supernovae and other violent events across the galaxy over billions of years. They travel through interstellar space in all directions essentially all the time. On Earth, the magnetic field and atmosphere reduce them to something negligible at ground level. On Mars, they reach you. The Curiosity rover has been measuring radiation on the Martian surface since 2012. The numbers it has recorded are between roughly 0.2 and zero point 0.7 millisieverts per day. Think about that for a moment. Earth's annual background is around 3 millisieverts per year. On Mars, at the measured surface rate, a person absorbs that same annual dose in somewhere between 5 and 15 days. Over a full Martian year, the accumulated dose runs approximately 25 to 80 times higher than an equivalent period on Earth. That is before a single solar storm arrives. The answer was stranger than expected. This is not the kind of radiation that drops a person on the spot. It is not acute. It does not burn skin or cause immediate sickness at the background rate. What it does is quieter and harder to undo. Each passing particle carries enough energy to break chemical bonds in DNA, to alter the molecular instructions that cells use to copy themselves, and repair damage. Cells have repair mechanisms for this. Those mechanisms are good, but they are not perfect. Every repair leaves the possibility of an error. Over months and years, those errors accumulate. The long-term result is an elevated cancer risk. Possible damage to bone marrow, which produces blood cells. Possible effects on the cardiovascular system. And at higher cumulative doses, possible impacts on the nervous system and the brain. Not a sharp injury. A slow account with compound interest. The solar storms add the sharp events on top of this. When the sun launches a coronal mass ejection, a swarm of energetic protons crossing space at high velocity, Earth's magnetic field catches most of them. What reaches the surface is a minor disturbance, some radio interference, an aurora at high latitudes. On Mars, with no magnetic field to deflect the incoming wave, and only thin air to absorb it, those particles strike the surface much more effectively. A person outside in a standard spacesuit during a major solar storm is not receiving a background dose. Within hours, the accumulated dose from a strong event can equal a full-body CT scan. In extreme cases, the dose climbs far beyond that. At those levels, the body responds in ways that cannot be ignored. Nausea, fatigue, the early signs of radiation sickness, and a substantial portion of a person's lifetime cancer risk, absorbed in a single afternoon. The critical question is not whether this happens. It is whether the shelter is adequate and whether the people inside can get to it in time. On Earth, a shelter from a solar storm is almost never needed. On Mars, adequate shielding is the architecture of every room, every corridor, every sleeping area. There is no outdoor location that is safe to wait in. Physical mass stops high-energy particles. Water works well. Thick plastic works. Rock and soil work. The math is straightforward, and the conclusions are demanding. To provide meaningful protection from cosmic radiation, a habitat needs at least tens of centimeters of dense material overhead. For strong protection against both the background and solar events, the requirement rises to roughly 1 to 3 meters of soil, somewhere between 3 and 10 feet of regolith, covering the roof and walls. Apply that to a habitat of 100 square meters, about the floor area of a modest apartment. 2 meters of Martian regolith overhead means hundreds of tons of material on top of the structure. 3 meters means many hundreds of tons. That mass cannot be casually placed. It must be mined, moved, positioned, and maintained by machines that are themselves operating in the radiation environment, accumulating damage in their own electronics and materials. This is where the glass dome disappears. The popular image of a Mars settlement has always included transparency. Large windows, open views of the sky and the landscape, perhaps grand domes of glass or transparent polymer letting in the sunlight. It is a natural image. It feels like what a human habitat should be. Transparent materials do not stop high-energy charged particles. A window that lets light through lets radiation through. A dome of glass or transparent polymer is not a radiation shield. It is an exposure surface. The honest architectural answer to Mars radiation is not a dome. It is a buried structure. Tunnels excavated into rock or compacted regolith. Underground rooms with a full meter or more of solid material overhead. At most, small viewing ports with heavy shielding framing for carefully limited time. The settlement that a radiation physicist would design for Mars looks less like a city and more like a bunker. A bunker where every person's accumulated dose is tracked the way a bank tracks a balance. where outdoor excursions are time-limited and logged, where an unscheduled extension of a surface walk carries a real cost counted in millisieverts added to a lifetime total. Now consider what a life at that baseline means over time. A complete mission, including months of transit through deep space in both directions and 1 to 2 years on the surface, accumulates a total dose that can push between 600 and 1000 millisieverts. Many current career limits for astronauts sit in that range. Those limits exist because doses in that range carry a measurably increased cancer risk and other long-term effects that extend decades into a person's future. A mission of 2 or 3 years is one thing. A permanent settlement is another. For a person living on Mars for 20 years, the steady galactic background alone, even inside a reasonably shielded habitat, will push the accumulated dose far beyond anything in current safety frameworks. Solar events add spikes on top of that steady accumulation. The nervous system, which may be more sensitive than other tissues to chronic low-dose radiation over decades, enters territory that has not been studied in humans at these doses and durations. The effects on the brain over a lifetime at Martian background levels are not fully understood. Long-term cognitive consequences are an open question. Some groups carry additional risk. Children absorb radiation more readily than adults because their cells are dividing rapidly during development. A child born on Mars and raised there would accumulate dose from infancy, in the most sensitive developmental window, with no period of low-dose reprieve like the one Earth's magnetic field provides from birth. Pregnant people face risk to the developing fetus during the most critical weeks of cellular organization. Older adults and people with existing conditions may find that chronic radiation accelerates processes that would have progressed slowly on Earth. None of these groups have an easy path home. Distance and cost mean that Mars is where they stay. Mitigation is possible. Underground construction, careful mass placement, early warning systems for solar events, strict dose management. These measures reduce the risk, but they do not eliminate it. Not to Earth levels, not without essentially living permanently inside a heavily shielded shell, and never emerging without adding to the count. Every kilogram of shielding had to be produced somewhere on Mars, moved by machinery, and installed by people who were accumulating dose during every shift of the work. The picture is not hopeless, but it is precise. Radiation on Mars is not something that happens to orbital astronauts managing career limits in low Earth orbit. It is something that happens to a person walking out their front door to check a sensor, breathing inside a habitat where the roof is several tons of compacted soil, watching their cumulative total rise through days and months and years with no possibility of stepping outside the accounting. And the body absorbing all of that radiation is the same body losing bone mass, managing a cardiovascular system calibrated to the wrong gravity, and sustaining every breath on machines that cannot be allowed to fail. The costs do not cancel each other. They compound. All of that compounds onto a body that still has to breathe, still has to eat, still has to work. And it compounds alongside something that does not stop at the walls. Even buried under meters of soil, there is one Martian threat that keeps finding its way through. Not from above, not from the radiation environment the rock overhead deflects. From the ground itself, from the surface just beyond the airlock door, lifted and carried and deposited by a thin atmosphere that never stops moving. The dust. This is not ordinary dirt. You cannot brush it off and move on. Martian dust is extraordinarily fine, with particles only a few micrometers across. That puts them in the same size range as cigarette smoke particles. And at that scale, particles are small enough to bypass the nose and throat entirely. They reach the deepest branches of the lungs, the passages the body clears very slowly, if at all. We have a preview of what this means. Apollo astronauts breathed a small amount of lunar dust that leaked into the lander after moonwalks. After only a few days, several reported what came to be called lunar hay fever, irritated eyes, scratchy throat, congestion. A few days of minor contamination left detectable symptoms. On Mars, exposure is not measured in days. It is measured in months and years. And it arrives not through one careless EVA, but through the accumulation of small failures. Every airlock cycle, every tracked-in particle, every minor seal imperfection discovered 6 months into the mission. The source of the contamination is the entire world just outside. But the size of the particles is not the only problem. Rovers and landers have found perchlorate salts throughout the Martian soil, at roughly 0.5% to 1% by weight. Perchlorates are compounds that interfere with the thyroid gland. The thyroid governs metabolism, growth, and energy balance. Even low-concentration chronic exposure is medically undesirable, and if perchlorate-laden dust finds its way into the habitat air, the water supply, or the food, the colony is not dealing with an acute poisoning event. It is dealing with a slow, chemical insult to hormones and health across the entirety of a long mission. This matters for food production in particular. The plan has always included growing food in Martian soil, but raw Martian dirt cannot simply be planted in. To make that soil usable, colonists would need to process tons of it, not kilograms, tons, washing it, treating it chemically, flushing out perchlorates and reactive salts, testing it for safety, then planting. That process demands water, energy, and equipment, all of them already scarce, all of them already claimed by other survival systems. What Earth provides nearly free, a thick layer of biologically active, largely benign topsoil, Mars charges for in industrial-scale chemistry before the first seed goes in. And then, there is what the dust does to machinery. On Earth, sand grains are rounded. Liquid water and centuries of abrasion smooth their edges over time. On Mars, there is no liquid water, no smoothing process. Dust particles at microscopic scale are sharp and jagged. They are abrasive. Every time a suited colonist walks back through an airlock, every time a joint flexes in a glove or a knee seal compresses, those particles are grinding. Over thousands of cycles, they open micro-grooves, widen gaps, erode materials that pass thousands of clean lab tests on Earth without failing. Low humidity and constant friction also make the dust electrostatically charged. It clings. It sticks to suit surfaces, visors, tool handles, solar panel glass. You cannot shake it loose, the way you would flick mud off a boot. It adheres and then it waits to be carried inside. This is why airlocks cannot simply be pressure corridors. They must function as full decontamination chambers, air jets to blast suits clean, vacuums to pull loose particles, possibly sticky surfaces or rotating brushes to capture what remains. Each of those subsystems draws power. Each must function in low pressure, in temperature cycling that cracks conventional materials, while being attacked by the same particles it exists to remove. Inside the habitat, protection comes down entirely to filtration, to duct design, to maintenance cycles followed precisely, even when a crew member is exhausted and behind on 3 other tasks. The colony breathes exactly as well as its filters perform. New filters, properly seated, work. But filters load with dust. Seals age. Someone installs a filter slightly crooked during a rushed maintenance cycle, and it passes 98% of particles instead of 99%. That 1%, over months, is particles reaching deep lung tissue, particles loaded with perchlorates and reactive compounds. The long-term outcomes from that kind of chronic inhalation are inflammation, higher risk of lung disease, and, over years, possibly cancer. All added to a body already managing bone loss, altered cardiovascular function, and accumulated radiation. The Martian surface is not a quiet, cold desert waiting to be worked. It is an active source of tiny, sharp, chemically reactive particles seeking every available path into lungs and machines. You cannot pave the planet. You can only manage how fast the dust enters and how well you remove it. Then the data shifted. That same dust is also the weather. The Martian atmosphere, thin as it is, never stops moving. Winds lift dust off the surface and carry it. Small whirlwinds pull it high. Local storms link together and grow. In some years, they do not stop growing. They wrap the planet. A global dust storm on Mars can last weeks, sometimes approaching 2 months. And during those weeks, the sky thickens until the horizon nearly disappears. Cameras on landers see a dim orange fog. Sunlight at the surface can drop by 90% or more. Think about what that means for power. Mars already starts at a disadvantage. The top of its atmosphere receives roughly 590 watts of solar energy per square meter. Earth receives about 1360. Mars gets less than half before a single cloud forms. Cut that already reduced figure by 90% with dust, and the light reaching the surface becomes a faint coppery twilight that persists all day, every day, for weeks. A solar panel farm that looked viable on paper stops being the primary power source. The panels are still there. They are still angled correctly. They produce a fraction of their normal output. Any settlement that built its energy architecture around heavy solar reliance is now running on borrowed time, rationing heat, air recycling, water processing, and communications against a shrinking reserve. One might expect that storms this dramatic must mean brutal winds, tearing equipment apart. Here is the reveal. Typical peak winds during large Martian storms run around 30 meters per second. That is approximately 110 kilometers per hour, roughly 70 miles per hour on Earth. Those numbers sound violent. On Earth, they would represent a severe windstorm. Rooftops at risk, trees down. On Mars, the atmosphere is about 1% as dense as Earth's. The same wind speed against the same surface area produces roughly 1% of the force. These winds generally do not knock down structures. They do not flip heavy rovers. What they do is more insidious. They are just dense enough and just fast enough to lift fine particles off the surface and keep them suspended, carrying them across continents, depositing thin layers on every exposed surface on the planet. The wind's power is not in pushing equipment over. It is in scraping it and blinding it and coating it with an even film of abrasive, electrostatically charged particles. And the coupled hardware failure that follows is precise. Radiators on the outside of a habitat or power plant are designed to dump waste heat into the Martian sky. They work by radiating infrared energy away from their surface. When dust settles on a radiator, it changes the surface properties. What was designed to radiate begins to insulate. Electronics running inside that system, already generating heat, begin running hotter, right at the same moment that solar panels are producing less power to run cooling systems. Power generation collapses precisely when thermal management demand rises. The two failures arrive together, and together they are worse than either would be alone. Managing solar panels on Mars therefore requires building a complete dust management ecosystem around them. Mechanical brushes to sweep surfaces clean, gas blowers to push particles off, possibly electrostatic systems to repel dust before it settles. Every one of those subsystems must function in low pressure, in temperature extremes, for years, while itself being slowly attacked by the same dust it is working to remove. Every one of them draws from the power budget already in deficit during the storm. Visibility loss compounds every other problem. Crews forced indoors for weeks, EVAs cut to genuine emergencies, construction halted, outdoor repairs delayed. Driving rovers in that orange fog risks disorientation, a lost landmark, a vehicle rolled or stranded far from any shelter. Landing new hardware during a storm becomes substantially more hazardous. Radar and optical sensors must see the ground accurately. Engines must manage blowing dust on final descent. The most complex operation in any mission profile becomes harder by a wide margin, precisely when supplies may be needed most. Even in normal years, without global storms, the baseline problem never goes away. Regional storms still cut solar input by meaningful percentages. Thin films of dust accumulate on panels between cleaning cycles. Filters load steadily. Power curves require constant monitoring. The systems that keep people alive on Mars are not simply built and trusted. They are watched, tended, and fought for, continuously. Mars weather does not merely inconvenience a colony. It directly attacks the main power source, interferes with thermal management, blinds navigation, and slows or stops surface work during the periods when every system demands more attention than usual. The sky periodically turns the dimmer switch down on the entire energy system and holds it there for weeks. And the dust that causes all of it is the same dust already working its way through the airlock seals. That is not the last of what the Martian environment imposes. The power system at the center of all of these cascading failures points toward a deeper problem. And that problem has been waiting beneath every assumption about living on Mars. That problem is the power foundation itself. Not the storms attacking it, not the dust coating it, the foundation underneath. Before any of that begins, start with a number. Mars receives roughly 590 watts of solar energy per square meter at the top of its atmosphere. Earth receives roughly 1,360. That ratio means Mars starts every single day with less than half the raw solar input available to the same panel area on Earth. No storms required, no dust layers required, just the planet's greater distance from the Sun, baked into physics, permanent and unchanging. A solar array sized to power a modest Earth outpost, replicated panel for panel on Martian soil, would produce less than half the electricity from day one. To match an equivalent Earth output, you would need more than twice the panel area, spread across harsh and dusty terrain before the first grain of Martian soil ever touches a collector surface. That is the floor. Everything that follows operates below it. Now add the nights. Martian nighttime temperatures routinely drop below negative 80 degrees Celsius, roughly negative 112 degrees Fahrenheit. Some nights reach lower. Battery chemistry slows in deep cold. Capacity drops. Internal resistance rises. Running a battery through charge and discharge cycles at those temperatures shortens its lifespan rapidly. This leaves the colony with two options, and neither is good. The first, burn power to keep battery banks warm inside insulated enclosures, protecting the storage system from the cold that makes it useless. The second, accept degraded performance and shortened lifespan, replacing batteries more frequently. Replacement means mass shipped from Earth. Mass shipped from Earth means launch windows and months of transit. Neither option escapes the trap. And what does the stored power actually need to cover through that long cold night? Life support runs continuously. Heating runs continuously. Water processing runs continuously. Communications run continuously. And the thermal management of the battery banks themselves runs continuously, using stored power to protect the very system holding the stored power. Underestimate the overnight load, and the system enters a spiral. Energy reserved to protect infrastructure gets consumed before the infrastructure can produce more. The machine meant to prevent the emergency becomes the machine driving it. This is why the obvious answer is nuclear. A compact fission reactor runs day and night. Dust storms do not touch its output. Cold does not degrade its performance. A few megawatts of steady thermal to electric power suddenly changes the arithmetic of every system in the colony. Heaters hold temperature. Water plants run around the clock. Ice mining equipment operates on a reliable schedule. The difference between a solar-only colony and a reactor-equipped colony is not a matter of convenience. But here is where it gets strange. Reactors do not grow on Mars. Every reactor, every kilogram of fuel, every control rod, every spare component must be built on Earth, qualified for spaceflight, launched, and shipped across roughly 225 million kilometers at opposition. That is approximately 140 million miles. The mass involved is large, the engineering is complex. Launch opportunities to Mars open roughly every 26 months. A reactor that fails or must be shut down does not get replaced by a generator on a diesel truck. It gets replaced by a multi-year waiting period, a new build, a new qualification campaign, and another months-long transit. In the gap between failure and replacement, the colony drops from a powered base to a cold, dark camp. The whole energy infrastructure rests on a small number of complex machines, each irreplaceable on short notice, each operating under radiation, dust, and cold for years without meaningful hardware support. Then, someone asks the reasonable question: what about backup fuel, the way a remote Earth station keeps a diesel generator and a tank of fuel for emergencies? The answer is a quiet reveal with large consequences. Mars has no oil, no coal seams, no natural gas. Fossil fuels are not simply scarce on Mars. They are absent as a concept. The planet never ran a billion years of biology to produce them. A chemical alternative exists. The Sabatier process can synthesize methane and oxygen from the carbon dioxide in the Martian atmosphere and hydrogen derived from water. The chemistry is real, but follow it through. Collecting water is already an energy-intensive operation. Splitting that water into hydrogen and oxygen uses electricity. Combining gases in controlled reactors uses equipment and power. The methane produced, when burned, returns only a fraction of the energy invested to make it. Locally manufactured fuel is not a free backup reserve. It is stored electricity, converted at a loss, available only if the grid was healthy enough to generate the surplus in the first place. When the grid is struggling and water production is marginal, there is no surplus to convert. Mars gives nothing free in the energy department. Every joule is paid for with infrastructure, complexity, and the ever-present risk of a part that cannot be replaced on any reasonable timeline. The stacked picture is this: less than half of Earth's baseline solar input. That input then dimmed by dust accumulation, that dimmed resource made worse during storms, all of it feeding into battery banks that degrade in deep cold, backed by reactors that must survive interplanetary shipping and years of operation, with minimal support, with no dense chemical fuels waiting underground. Water extraction, air processing, heating, radiation shielding, mining equipment, and transport vehicles all rest on this foundation. When the foundation wobbles, the chain tightens link by link. Long dust storm, solar output drops, batteries weaker than normal, heaters throttled back, ice mining slows, water production falls, air recycling margins shrink, not loss of comfort, risk of crossing the threshold where one more small failure becomes the one that pushes everything over. Which brings the conversation directly to water, because water is the clearest example of how that fragile power foundation translates into the details of daily survival. People say Mars has water, and technically they are right. The planet holds significant quantities of ice. But water as a map label and water as something a human can drink are separated by an enormous gap of energy, equipment, and chemistry. Most of the accessible Martian water is locked as ice. The clearest, shallowest deposits are concentrated at high latitudes, closer to the poles. But high latitudes on Mars are colder, darker for much of the year, and harder to supply with reliable power. The lower latitude zones preferred for landing, relatively flat and temperate by Martian standards, tend to have water ice buried under dry regolith, anywhere from tens of centimeters to several meters down, mixed with dust and reactive salts. Not a well. Not a spring. A mining operation for frozen salty mud. The equipment required reflects this reality. Excavators to remove overlying material. Drills to break the frozen layer. Heaters to begin extraction. Grinders to process the ice-bearing regolith. Conveyors to move material. Every link in that chain runs on power and runs every day, because the crew never stops needing water, and crops never stop needing water, and the life support system never stops needing water. Here is the energy cost. Ground ice on Mars sits at roughly negative 80 degrees Celsius. To produce usable liquid water, that ice must be heated to 0 degrees Celsius, melted, and then kept above freezing throughout the cleaning process that follows. That temperature climb from negative 80 to 0 across a mass of ice mixed with soil requires hundreds of kilojoules of energy per liter of water extracted. A small outpost, a few people plus food production plus basic industrial use, needs hundreds to thousands of liters per day. Multiply that daily volume by the energy cost per liter, and the result is a substantial fraction of the colony's total daily power budget, committed to one task: moving frozen dirty water to liquid clean water, before any other system draws a watt. And melting the ice does not solve the chemistry. Martian ice and the surrounding soil carry perchlorates. They carry other salts. Melted ice is not safe water. The colony must run a continuous water treatment plant inside the habitat. Pumps and filters and reaction tanks and sensors and storage vessels and control systems, all operating without major failure and all consuming parts that wear out. Filters clog, catalysts age, Sensors drift and need recalibration. Every maintenance job on this equipment is a chance for a mistake in an environment where a mistake in water chemistry poisons people slowly and without obvious announcement. The picture did not hold in a different way than the energy cost. On Earth, water that spills, evaporates, leaks, or gets vented returns to the environment and cycles back eventually. Mars cannot do that. The thin atmosphere and weak gravity mean that water vapor escaping from a vent, moisture lost in dumped wastewater, water in the exhalation of every breath, all of it drifts towards space and does not return. The planetary water cycle on Mars operates on a thin sublimation process, ice to vapor directly, and even that vapor gradually leaks away. Colony water is a bank account with a slow, limited income and many routes to permanent spending. Every inefficiency, every small leak unfixed, every minor vent unclosed, subtracts from a total that does not automatically replenish. Shipping water from Earth is not a realistic answer. Every kilogram launched from Earth carries an enormous energy and financial cost attached to it. Long-term resupply of bulk water is not a viable strategy for any settlement planning to persist. Local extraction and recycling must work under harsh conditions, with equipment under constant stress, without failure. The two problems lock together at the bottom. The water economy depends entirely on the power foundation. The power foundation is already running at a deficit before any storm arrives. Every litre of water a colony needs is a direct claim on that same strained power budget. And when the power budget tightens because of a dust event or a battery cycling problem or a reactor maintenance cycle, the water production line is among the first systems to feel the reduction. Mars has water. What that sentence does not tell you is whether a colony can drink. And the question of what a colony can eat from Martian soil, which depends on that same water and that same power and the same chemically hostile ground, points toward a problem that compounds both. That question about what a colony can eat sits inside a larger one. Not just whether the food grows, whether the entire system sustaining the food, the water, the air, and the people can hold together every hour, without a break, for years. And when you pull back far enough to see the whole picture, something becomes clear that the dream of Mars rarely makes room for. You do not live on Mars. You live inside a machine, and the machine must work every second. On Earth, the life support system is the planet itself. Oceans absorb and release heat. Forests pull carbon dioxide out of the air and return oxygen. Rivers carry waste downstream. Rain cleans the atmosphere. Soil filters toxins through biological processes that have been running for hundreds of millions of years. When you exhale, the planet handles what comes next. You never have to think about it. You never have to schedule it or repair it or power it through the night. None of that exists on Mars. Every cycle is mechanical. Pumps move air through scrubbers. Filters pull contamination from water. Reactors and bioreactors grow algae and microbes to close nutrient loops. Everything that Earth does through sheer biological inertia, a Mars colony must do on purpose, continuously, with hardware. And hardware fails. The air loop shows this most clearly. Oxygen must stay within a narrow range. Too low and people become confused and slow before they realize anything is wrong. Too high and materials become fire hazards. Carbon dioxide must stay below a hard limit. Humidity must be managed. Trace gases must be monitored. A misread sensor, a pump running 5% slower than it should, a scrubber cartridge that has reached the end of its life and has not yet been replaced. Any one of these is enough to start a quiet drift. The problem does not announce itself with an alarm at the first moment. It announces itself when someone has a headache they cannot explain, when a crew member feels slow and does not know why. By then, the system requires active intervention. But something was wrong. The fix must happen while breathing the air that depends on the failing system. There is no other air. Opening a window is not an option. Outside is cold, nearly airless, and 95% carbon dioxide. The repair and the emergency are simultaneous. Water follows the same logic. Every drop in the system has been mined from frozen ground, heated at considerable energy cost, filtered, and tested. It circulates through drinking lines, hygiene, food production, cooling loops, and industrial processes. The water a colonist drinks in the morning may have passed through a cooling radiator and a hydroponic tray in the past week. A clogged filter that ruptures, a chemical dosing pump that misfires, the wrong microbial population establishing itself in a holding tank. Any of these can contaminate a large fraction of the stored supply in hours. On Earth, a contaminated water batch is a serious problem with serious solutions. Drain it, dilute it, replace it from another source. On Mars, draining the supply means losing days of mining and melting work, and accepting a smaller reserve while the system is rebuilt. You cannot call a water utility. Food adds another layer on top of both. Long-term presence on Mars cannot depend on shipments from Earth to cover calories. The mass and the cost are simply too large. Greenhouses, algae tanks, and microbial reactors have to grow a real fraction of what people eat, and they have to close the nutrient cycle by converting human and biological waste back into plant inputs. This requires light, water, controlled temperature, a carefully balanced microbial community in soils or solutions, and the constant management of competing organisms. A single pathogen introduced into a greenhouse, a mold outbreak that moves through trays before it is identified, a nutrient balance that drifts without obvious early signs, a lamp array that begins failing. Any of these can wipe out a crop cycle. On Earth, a failed harvest in one region is covered by global agriculture and supply chains. On Mars, the colony's main greenhouse is the supply chain. A failed cycle is a direct hit to food availability months downstream when the next crop would have been ready. And the reason you cannot simply bring more redundancy to address all of this is that getting mass to Mars costs enormously. Pushing 1 kilogram from Earth's surface to low orbit requires roughly 9.4 kilometers per second of velocity change. Sending that kilogram onward to Mars requires several more kilometers per second on top. The physics do not negotiate. Every extra kilogram of spare pumps, backup filters, redundant sensors, or emergency rations must be accounted for during mission planning, funded, built, tested, and launched at exactly the right time during a transfer window. That window opens roughly every 26 months. If the wrong equipment was prioritized, or a critical spare was not included, the wait for correction is not days or weeks. It is the next window, which is more than 2 years away. This means every kilogram is a genuine trade-off. An extra water pump against an extra air filter. More reactor components against more medical equipment. Additional shielding mass against additional greenhouse equipment. There is no option labeled bring enough of everything. The mission flies with whatever the planning process prioritized, and the colony lives inside those choices. The long-term escape from the resupply trap is bioregenerative life support, using plants, algae, and microbes to close the loops so completely that almost nothing needs to come from Earth. In principle, this is the answer. In practice, no system like this has ever been run at the scale of hundreds or thousands of people, over decades, with the full messy reality of human biology, disease, equipment failures, and unexpected interactions. The International Space Station recycles water and scrubs air, but it still depends heavily on Earth resupply for food, replacement parts, and critical consumables. It is the closest thing we have to a testbed, and it has not closed the loop. On Mars, if the internal ecosystem crashes, if the balance of gases, nutrients, and microbes inside the bioreactors flips in the wrong direction, there is no planetary reservoir to draw on. Recovery means flushing tanks, regrowing cultures from frozen backups, replanting greenhouses, and living on emergency rations and bottled oxygen while waiting for systems to stabilize, with limited spare parts and a power budget already under stress. In this environment, maintenance is not a task. It is the colony's identity. Every pump, valve, circuit board, sensor, and seal in an air duct must be inspected on a schedule, cleaned, calibrated, replaced before it fails rather than after, and logged so that the next inspection knows what was done. On Earth, a broken ventilation fan in a building is an inconvenience. Outside, air leaks in, people prop a door open, and someone calls a service number. On Mars, a broken fan in the wrong subsystem creates stale pockets of air, rising carbon dioxide concentrations, or dead zones in a greenhouse where plants begin to lose oxygen production within a day. The colony is more accurately described as a team of operators running a planet-scale industrial facility whose only product is survival. Everyone is part colonist, part mechanic, part emergency responder, and human beings, inside closed systems under sustained stress, make errors. Fatigue produces skipped inspections. Alarm fatigue produces overridden warnings. A mislabeled filter gets installed in the wrong housing. A fitting is tightened to 90% of the required torque, and the vibration does the rest over the following weeks. On Earth, small errors wash out into a forgiving environment. The outside world absorbs them. On Mars, they accumulate in a system with almost no slack. One overlooked pipe crack leaks water into a wall cavity slowly. One miscalibrated sensor underreports carbon dioxide by 15% until the first crew member reports a headache, and the alarm has still not tripped. But the machine problem does not stop at pumps and sensors. It extends into the biology traveling inside it. You are not sending people to Mars. You are sending ecosystems. Every person carries trillions of bacteria, viruses, and fungi in the gut, on skin, and in the airways. This microbiome evolved over millions of years, calibrated to one gravity, normal radiation levels, a varied diet, and constant exposure to new people and new environments. On Mars, all of that changes simultaneously. Gravity drops to 38% of what the microbiome has always known. Radiation rises substantially. Diet shifts toward packaged food, hydroponic crops, and processed water. The air is recycled. The same surfaces, the same people, the same environment repeat day after day for years. The immune system, tuned to a particular pattern of microbial contact, can overreact or underreact when that pattern changes this completely. Gut bacteria shift with processed and shelf-stable food inputs, as some species become more dominant and others shrink from reduced fiber and fresh material. This matters more than digestion alone. The gut communicates with the nervous system through chemical and immune signaling. Shifts in the gut microbiome have documented effects on mood, cognition, and mental health. On top of the physical demands, the isolation, the confinement, and the constant operational pressure, the colony's internal biology is running a slow experiment with itself. Higher radiation adds another layer. Radiation damages DNA, and not only human DNA, microbial DNA. A pathogen circulating in a small, stressed, irradiated community lives in an environment that pushes it toward change. Mutation rates rise. Variants can emerge with symptoms or resistance patterns that have no precedent in Earth medicine. On Earth, a virus spreading through a city infects millions, builds population immunity, and burns out. The population is large enough to absorb it. On Mars, the same virus has nowhere to disappear to. It cycles through the same small group, returning when immunity wanes, waiting for new arrivals. There is no seasonal reshaping, no fresh air mass from another continent, no herd immunity at meaningful scale. And then there is the contamination question that runs in both directions. Space agencies work hard to sterilize probes sent to Mars, precisely to avoid seeding an alien environment with Earth biology before we understand what is already there. Humans make that precaution irrelevant the moment they land. Breathing, sweating, shedding skin cells, managing waste. The local environment is seeded with Earth life continuously, regardless of protocol. The reverse concern is not zero either. If Mars harbors any native microbial life in certain soils or subsurface ice, bringing those organisms into warm, pressurized, nutrient-rich habitat air could end in two very different ways. They might encounter Earth chemistry and die, or the conditions, far more favorable than a frozen Martian surface, might allow them to adapt and grow. New biofilms, unexpected corrosion patterns, interactions with Earth microbes that no laboratory has ever tested. The crew and their habitat become a continuous live experiment with no time out. Medicine sits at the end of all of this with the smallest margin. On Earth, a serious medical case escalates. A small clinic refers to a hospital. A hospital calls a specialist. A specialist orders imaging that requires a machine the size of a room. Surgery draws on a team, a blood bank, sterile equipment replaced after every use. On Mars, the hospital is whatever was packed into a lander and installed in the habitat. Complex surgery after a low-gravity spinal injury faces limited tools, limited blood supply, limited sterilization capacity, and possibly one person with surgical training who completed that training years ago and has not performed that specific procedure since. Cancer means basic diagnostics and limited treatment options. No radiation therapy at meaningful clinical scale. No specialized drug protocols designed for the full range of presentations. Infections involving mutated microbes in a closed, irradiated system can be reported to Earth, but even at the closest alignment between the two planets, a signal takes several minutes to arrive. There is no real-time consultation. Every decision is made in the room, by the people in the room, with what those people have. The hard cases compound this. There are no donor organs, no flight to a better equipped facility, no clinical trial population large enough to generate reliable data about what works. And the patient is someone the rest of the crew works with every day, whose absence changes operational capacity and hits morale in ways that cascade through the rest of the system. Even routine care is harder. Dentistry in low gravity requires adapted tools and techniques. Pregnancy and childbirth at 38% gravity have no tested playbook. Chronic conditions like diabetes and heart disease operate in a different fluid environment with a higher radiation background and an altered gut microbiome. And the extrapolations from Earth medicine are guesses in the places that matter most. When the guess is wrong, the patient cannot be sent home. The next transfer window is roughly every 26 months. The trip itself takes months. Neither option is rapid. What you are left with is not an address change from one planet to another. It is a complete replacement of the biological context the human body expects, in every direction at once, with a medical system small enough to fit in a cargo hold and no real exit route if the wrong thing goes wrong. And the people living inside this machine, breathing its air, eating its output, and depending on every seal and sensor to hold, are also being changed by the machine itself in ways that will not be fully visible for years. That is still where we left the biological story. The body being changed, the machine running, the no exit condition already established. But there is another layer to the no exit condition, and it has nothing to do with failed seals or bone density. It has to do with what the mind has to live with, day after day, for years. Think about what Mars actually feels like from the inside of that machine. The first thing that changes is communication. At closest alignment, a signal traveling at the speed of light takes roughly 4 minutes to cross from Earth to Mars. At the far end of the orbit, when the two planets swing to opposite sides of the Sun, it is more than 20 minutes one way. A simple exchange, a question and an answer, consumes 30 minutes of waiting. There are no real-time voice calls. No one picks up the phone. What exists instead is something closer to very slow text messaging, where you send a message and wait, and by the time the reply arrives, the mood that prompted it has passed. The crisis has moved on, or you simply no longer want to talk. The person on the other end said something thoughtful and kind, and it lands 4 minutes later into a different emotional moment than the one it was meant for. Support does not disappear. It becomes physically distant and functionally disconnected in a way that no video call or letter quite replicates, because the delay is built into the physics. There is no technology that fixes it. The speed of light is the ceiling. The physical world shrinks to match. A few pressurized modules, a network of connecting tunnels, a rover. Beyond the airlock, an operational zone that will kill you in minutes without full gear. Not an outdoors, not a place to walk to clear your head. A lethal surface you access in a full pressure suit for work, not for rest. On Earth, the brain resets constantly without effort. Changing light through a window, a stranger passed on a sidewalk, rain on a different day, the minor accidental variety of any 24 hours. None of that exists on Mars. Same walls, same filtered air, same hum of pumps and fans, same small group of faces at every meal. The brain uses variation as a stabilizer, and when variation is stripped away, the mind starts to smooth the days together. Time is marked by checklists and mission logs rather than by felt experience. Weeks blur. The same routines run again and again inside the same narrow set of rooms. All of it against the background awareness that the machinery keeping you alive has not yet failed, but could. That small group of people becomes its own pressure system. A few dozen individuals in a closed space, under sustained risk, with strict schedules, and nowhere to step away. One difficult personality on Earth can be avoided. You change subway cars. You eat at a different restaurant. On Mars, they are present at every meal, every drill, every maintenance shift, every unscheduled alarm at 2 in the morning. Arguments have no room to diffuse. Grudges are not diluted by a wider world. A disagreement over something small, a shared chore, a scheduling conflict, does not dissolve into the ordinary noise of life. It sits at the table again the next day. Group dynamics that would sort themselves out in a normal social environment can lock into rigid patterns with no external pressure to break them. And stress amplifies all of it. Long hours on critical systems, sleep broken by alarms, no real weekend, no flight home to see family, nothing that functions as a genuine pause. The conditions that generate depression, anxiety, and chronic irritability are not incidental. They are structural. They are the baseline conditions of the experiment. Unless enormous effort goes into crew selection, long-term psychological training, robust mental health support, and clear governance frameworks, the social environment will eventually produce exactly what those conditions produce. There is a particular quality to the stakes that adds another pressure no one outside can quite replicate. Walk the habitat, and you pass life support panels, radiation monitors, pressure gauges. The instrumentation that tells you the wall between you and the Martian surface is still holding. On Earth, risk is mostly abstract. The plane you're on might fall. The building you're in might burn. Most people do not think about it while it is not happening. On Mars, the reminder is physical and constant. Everyone you know on the planet is inside the same pressurized envelope. A major failure does not kill a stranger down the street. It kills everyone. That awareness does not have to be spoken aloud. It is visible on the walls of every room. That is when the pattern broke. Even if someone reaches the breaking point, even if the social environment fractures beyond repair, even if an individual's psychological state deteriorates to the point where they cannot function, the option of leaving does not exist on demand. On Earth, you can quit, you can move, you can walk out. On Mars, the words, "I want to go home," are not actionable. Not quickly, not alone. Return launch windows open roughly every 26 months, when Earth and Mars realign in their orbits to allow an energy-efficient transfer. Miss a window and wait more than 2 years for the next one. Even when the window is open, a fueled return vehicle must be available, and the program must authorize the departure. The person in distress is locked, emotionally and physically, into the experiment. If the environment is wrong for them, if the social group is incompatible, if the risk eats at them every hour, the options narrow to 2. Keep going. Or break. Problems that would be tolerable for a season on Earth, because they come with an end date and an exit, become something heavier when they stretch for years with no guaranteed exit visible. And then grief adds to all of it. If someone dies in an incident, there is no wider society to absorb the loss. No community outside the group to hold the weight. No funeral that does not include the same people who also need to be back at their posts within hours. Life support does not pause for grief. The CO2 levels do not stop rising while people process what happened. The systems still need running. The work still needs doing. Every person in the group carries the loss and the operational pressure simultaneously, in the same small rooms, looking at the same walls. Now, consider that this is also a physics problem. The 26-month window is not a scheduling convention. It is the synodic period of Earth and Mars, the interval at which the two planets realign for an energy-efficient transfer. Earth and Mars orbit the Sun at different speeds. They converge into favorable geometry approximately every 2.1 Earth years. The physics does not adjust for budget cycles, mission schedules, or personal crises. When the window closes, it closes. Even within the window, the transit is not quick. A Hohmann transfer orbit, the standard energy-efficient path between two planets, takes roughly 6 to 9 months one way. 6 to 9 months inside a cramped vehicle in microgravity, with a radiation environment actually higher than the Martian surface because deep space has no atmosphere for even partial shielding. If something goes seriously wrong during transit, the nearest help is a radio signal delayed by minutes, and the only tools available are what was packed on board. No one is dispatching a rescue. The trip is the prologue. It comes before the years on the surface. Outside the transfer window, emergency resupply is not a plan that exists in any practical sense. A small, fast probe with a minimal payload can be sent on a high-energy trajectory outside the standard window. Tons of food, filter replacements, or reactor components cannot. Fast evacuation is not a concept that applies to Mars, except within the narrow alignment intervals. The phrase, "we can send help," is only true approximately once every 26 months, and only if the help was already being prepared. Underneath all of this is delta V, the total change in velocity a spacecraft must achieve to complete a journey. Escaping Earth's gravity requires roughly 11.2 kilometers per second, a speed most people cannot picture but can feel in the energy budget of every kilogram that attempts it. Additional delta V is needed to shape the orbit across interplanetary space, rendezvous with a transfer vehicle, and match Mars's velocity on arrival. Reusable rockets reduce the cost per launch. They do not change the physics. Every kilogram still has to climb out of a deep gravity well, cross tens of millions of kilometers, and be slowed precisely enough to reach the surface intact. Mars is not far only in distance. It is far in energy per kilogram, and that distinction shapes every single design decision before anyone leaves the ground. Because every kilogram has to earn its place. There is no extra manifest. A thicker module wall is more shielding, and also more launch mass. A better exercise machine fights bone loss and also takes payload space from something else. A secondary water recycler as backup means something else is left behind, or waits for a later mission that may or may not arrive on schedule. The trade-offs are not abstract. They are forced, upfront by physics, and the consequences of the wrong choice arrive on a 26-month clock. If a key cargo shipment is lost en route, the architecture that was counting on exactly those components has no rapid way to recover. Mars is not a continent reachable by container ship. It is a moving target across interplanetary space, lining up at specific intervals, behind a deep energy barrier that does not shrink because the mission needs it to. That barrier shapes the logistics, and the logistics shape the inner life. The no-exit pressure of the mind that we start with is not a coincidence of the environment. It is literally enforced by the orbital mechanics. The physics that governs the window is the same physics that keeps the exit locked. The two problems are one problem. And the builders of any serious Mars architecture have to design for both at the same time, before the first person steps into the lander. Because once the window closes, the design is the design, and the people inside it are committed to living with what it actually is. What they will be living with goes deeper still. Because underneath all of it, underneath the pressure suits and the water plants and the buried bunkers and the orbital windows, there is one more reply that keeps surfacing. One more answer that people reach for when every other argument has run out. We will change the planet itself. We will terraform Mars. We will pump greenhouse gases into the sky, warm the ground, thicken the air, and eventually build a world where humans can breathe. It is a compelling idea, and it does not survive contact with the numbers. The simplest version of the plan centers on carbon dioxide. Mars has CO2 locked in its polar ice caps, and loosely bound in the surface regolith. CO2 is a greenhouse gas. Release enough of it, the thinking goes, and the atmosphere thickens, temperatures climb, and the planet edges towards something livable. The reading came back reversed. Studies of the poles and the soil show that if you vaporized every accessible reserve of CO2 on Mars, every gram available in the caps and the shallowly trapped layers, the resulting atmosphere would reach only tens of millibars of pressure. Earth's sea level pressure runs around 1013 millibars. Tens of millibars is still near vacuum territory. No lakes appear. No rivers form. No stable liquid water sits open under a clear sky. You could not walk outside in a jacket without a mask. The numbers are not close. They are not in the same conversation. Even importing extra gases from elsewhere does not save the plan. The problem is not just quantity. The problem is that Mars cannot hold a thick atmosphere. Earth wraps itself in a global magnetic field, generated by the churning of its molten iron core. That field deflects the solar wind, the continuous stream of charged particles flowing outward from the sun. Mars's core cooled billions of years ago. The field collapsed. What remains are weak, patchy remnants in ancient rock, not a planetary shield. The solar wind reaches the upper atmosphere directly and strips gases away to space. Orbiting spacecraft have measured this process. It is not a theory about the distant past. It is happening now, continuously. Every day the sun shines. Any thick atmosphere you built on Mars would leak. Not slowly, in the comfortable sense of leaking. Steadily, predictably, and without stopping. Keeping Mars warm would be like trying to heat a house where every window is permanently cracked and the front door never fully closes. You could pour energy in continuously and still fall behind, and that forces the timescale question into the open. Serious models of planetary scale terraforming, the kind that account for atmospheric chemistry, heat transfer, and ongoing solar wind loss, place the effort in the range of thousands to millions of years of sustained planetary engineering. For comparison, modern industrial civilization, the civilization capable of even imagining terraforming, is 1 or 2 centuries old. The longest running continuous human institutions, the ones that have not collapsed, fragmented, or transformed beyond recognition, last a few hundred years at most. Proposing to terraform Mars means proposing a project 10 times to 1,000 times longer than any system we have ever maintained. It assumes that descendants through wars, famines, technological revolutions, and cultural transformations will keep feeding energy and resources and attention into the same planetary scale effort on a near geological timescale. There is no evidence that human civilization can sustain that focus. There is substantial evidence that it does not. So the fantasy quietly shrinks. Not a terraformed world with open skies and breathable air. Domes. But a dome is not a transformed planet. A dome is a spacecraft bolted to the ground. Under a dome, you still manage pressure walls, air scrubbers, water treatment, power generation, radiation shielding, and dust. The red desert outside is exactly as deadly as it was before the dome went up. You have not changed Mars. You have built a bubble on top of it, and the bubble introduces its own failure logic. A small, thick-walled habitat is easier to monitor, repair, and shield. A large, transparent dome is harder to protect from impacts, harder to shield from radiation, and far harder to repair when something goes wrong. One structural crack and a huge pressurized volume tries to escape into near vacuum. That is not a gentle failure mode, not a slow leak, a catastrophic one. Even inside the dome, even granting the dome works as intended, the ground underneath is not perfectly stable. Mars looks quiet from a distance, geologically ancient, geologically settled, but the InSight lander has detected Marsquakes reaching up to roughly magnitude 4 at the surface. On Earth, a magnitude 4 quake rattles dishes and startles people and is forgotten by morning. On Mars, the surface is largely rigid, brittle regolith and fractured rock, not the thick, softened soils that absorb seismic energy on Earth. More of the motion reaches structures directly. A small quake that twists a habitat ring or stresses a tunnel junction can open microfractures in pressurized seals. The repair and the emergency arrive simultaneously, as they always do on Mars, and the ground keeps moving in slower ways too. The seasonal frost cycle, water ice and CO2 freezing and sublimating in annual rhythm, shifts material near the surface year after year. A pipeline or a row of connected modules sitting on ground that gains and loses ice in its pores will tilt slowly, settle differentially, put strain on joints and connectors. Over a decade, combined with thermal cycling and dust erosion, things move out of specification. The surface is not a static platform. It is a slow, random hazard generator. Add dust devils, tiny vortices individually undramatic, but thousands of passes across the years scour paint, abrade coatings, work grains into new positions, add small impacts. Earth's atmosphere burns up most of the rock that hits it daily. Mars's thin air does not generate enough friction and heating for small objects, and fresh craters appear in orbital images taken decades apart. Near a base, that means debris, shock waves, added dust layers, and terrain that no longer matches the maps the first landing parties made. All of it together means that even the dome-based plan, the plan that gave up on changing the planet and settled for surviving on top of it, requires constant over-engineering just to stand still. Deeper foundations, more flexible joints, redundant seals, ground surveys repeated with radar on regular schedules, critical systems spread out so one event cannot take all of them. Enormous effort, continuously applied, whose only product is not falling apart. That forces the economic question. Shipping 1 kilogram from Earth's surface to the Martian surface, accounting for launch, interplanetary transit, orbital braking and landing, costs tens of thousands of dollars per kilogram, even under optimistic assumptions. A human being is not 70 or 80 kilograms. A human being on Mars is a share of habitat volume, structural material, life support hardware, shielding mass, food supply, water supply, suits, tools, medical equipment, and engineering margin. That share runs into tens of tons, tens of thousands of kilograms per person. Multiply tens of thousands of dollars per kilogram by tens of thousands of kilograms, and each colonist arrives as a multi-billion-dollar logistics package before they have done a single hour of work, before any resupply, before any emergency, before the first hardware failure, and the maintenance line never ends. On Earth, a town eventually becomes economically self-sustaining because the environment cooperates for free. Air, rain, soil, and pressure already work. On Mars, every life-enabling kilogram must be purchased, built, and thrown across interplanetary space. Critical pumps, specialized electronics, reactor components, medical devices, and sealed bearings cannot easily be manufactured from raw Martian rock without factories that themselves require machines and feedstock and power and people. So a cargo stream keeps flowing every 26 months with high-value items needed just to stay at the same capability level. Miss a few cycles, absorb a major technical failure, or face an economic crisis on Earth, and the chain breaks. The settlement does not coast gracefully. It begins to degrade. Systems move from fully functional to barely functional. Redundancy is consumed. Safety margins narrow. The idea that a Mars city eventually stands on its own feet ignores that the planet provides none of the background support. The maintenance bill does not shrink. It grows with the population. And behind the economics are people. You are not sending machines. You are sending people who feel pain, form relationships, and have children. One major system failure, power, air, water, or shielding, can mean mass casualties within hours. A design mistake or a management error does not produce a bad quarter. It can erase a community. Is it ethical to ask people to sign up for that, especially when the plan quietly assumes some will never return? A one-way mission means not just working far from home, but dying there. When children are involved, the question sharpens considerably. A child born on Mars does not choose 0.38 G, elevated radiation, sealed habitats, or a world where the outside air is poisonous. They inherit it. Their biology, shaped from infancy by Martian gravity and Martian radiation loads, may adapt so completely to those conditions that Earth's gravity becomes dangerous for them. We covered what that means earlier. The permanent heavy backpack that every step on Earth would feel like. We would be creating humans who may never safely visit the planet their ancestors came from. And for those who did choose to go, consent does not stay fixed across decades. Someone in their 20s might genuinely, freely accept a high-risk permanent assignment on a hostile world. That same person at 40, after years of hardware failures, dust storms, broken sleep, and crew conflict, has no rapid way to revise the decision. Return windows are 26 months apart. Return vehicles are scarce and expensive. The exit is not locked by malice. It is locked by physics. But locked is locked. The honest framing is this: Mars is not a backup Earth waiting to be claimed. It is not an escape hatch from climate change, resource crisis, or war. Treating it that way is backwards. If we damage Earth badly enough to make it uninhabitable for most life, Mars will not save us. Going from a warm, damaged Earth to Mars would be like walking out of a leaky but heated house in winter and climbing into a broken refrigerator outside. You might rig heaters inside the refrigerator. You might survive for a while, but you are in a box fighting the outside environment every second, with no margin for the next failure. From a scientific point of view, a small, carefully supported human presence on Mars might be worth the cost and risk. We would learn things no other way. How life behaves under chronic radiation. How closed ecosystems hold or collapse at multi-year scales. How societies function in permanent confinement with no external world to appeal to. Those are genuine questions worth genuine resources. But calling that a new home for humanity is not accurate. It is a permanent survival experiment on a hostile planet, with a price tag so high and a risk profile so sharp that only a tiny number of people will ever experience it directly. Most of humanity will never live there. Most of humanity could never live there. When you hear that Mars is where we will go if we ruin Earth, the answer is simply no. Mars is where a few of us might go to understand how narrow the window for human life actually is. How much work the planet we already have is doing, invisibly, every second, without a maintenance crew, without a power budget, without a repair log. For everyone else, and for any serious future for our species, the planet that actually matters is the one we are standing on now. The one that does all of this for free.